Welcome to Talk Tensors. I'm your host, and I am genuinely vibrating with energy for today's session. We're doing something a little different, something that I think is going to fundamentally change how you look at that chatbot tab open in your browser.
Oh, I'm excited for this one.
Usually we look at the big flashy model releases, the GPT-4s, the Geminis, the massive parameter counts. We obsess over the engine size.
We do. We're all guilty of that.
But today, we are looking at the plumbing. We are looking at the architecture of how these models actually think.
It is good to be here. And you are so right. The plumbing is where the actual revolution is happening right now. We are moving past the era of just make the model bigger and into the era of how do we make the model behave like an agent.
Yeah.
It is the difference between having a Ferrari engine and knowing how to drive it on a racetrack versus just, revving it in a parking lot.
Exactly. And the paper we are covering today is foundational to that shift. It's titled Tree of Thoughts, Deliberate Problem Solving with Large Language Models.
A classic out of Princeton and Google DeepMind.
And let me tell you, if you have ever felt like your chatbot is just kind of rambling without a plan, or if you've seen it confidently lie to your face about a math problem, this paper explains exactly why that happens.
And more importantly, it proposes a fix. It really does. It addresses this central tension in modern AI. We have these incredibly powerful large language models, but they are they're fundamentally limited by what we call their System 1 nature.
Okay, let's unpack that right away. System 1 versus System 2. This is Cognitive Science 101, right? We're talking Daniel Kahneman here.
Precisely. In human psychology, System 1 is your fast, automatic, intuitive thinking. It's when you see a face and instantly recognize it as your friend, or when someone asks you, what's 2 plus 2, and you say 4, without even really processing it.
It's a reflex.
It's associative, a reflex.
That's the gut feeling. It's
right.
Walking down a familiar street.
Right.
You aren't navigating. You're just moving.
Yes. But then there's System 2. And System 2 is slow, it's deliberate, it's conscious. It's what you use when you are solving a long division problem or planning a complex travel itinerary or trying to write a mathematical proof.
You have to stop.
You have to stop, plan, evaluate, and maybe even backtrack if you make a mistake. It requires effort. You can literally feel your pupils dilate when you engage System 2.
And the argument here, the core thesis of this paper, is that current LLMs, even the best ones, the ones we pay $20 a month for, are stuck in System 1.
That is the core problem definition. Think about how an LLM generates text. It is autoregressive.
Okay, there's the technical term. Let's break that down.
It's a fancy term, but it just means it generates token by token from left to right. It looks at the sequence of words that came before, it calculates the statistical probability of the next word, picks one, and moves on.
And that's it. It commits.
Once it outputs a word, it is committed to that word.
Yeah.
It can't stop, delete the last 3 sentences, and say, actually, that reasoning was flawed. Let me try a different angle. It just keeps rolling forward.
It's like improv comedy. The first rule is yes and. You can never say no, wait. You have to accept whatever craziness came before and just build on it.
That is a perfect analogy. And for creative writing or brainstorming or, just chatting, yes and, is fine. It's actually great. It feels fluid.
But for math.
For coding, for logical puzzles where there is a strict right and wrong, yes and is a disaster.
Because if you make a mistake.
If you make a mistake in the first step of a math problem and you just keep generating based on that mistake, you are hallucinating confidently into a wall. You are building a skyscraper on a swamp.
So this paper, Tree of Thoughts, is proposing a way to give these models a System 2. A way to stop, to think, and to look around before committing to the next step.
Exactly. The thesis statement of this work is that true problem solving requires exploring multiple reasoning paths, self-evaluating those choices, and looking ahead or backtracking. They are essentially turning an LLM from a simple text generator into a search algorithm for reasoning.
A search algorithm for reasoning.
They are forcing the model to deliberate.
I love that phrasing. So before we get into the tree part, let's look at the before times. What were we doing before this paper? Because we didn't just jump from 0 to this, right?
No, not at all. Well, the baseline is just input-output prompting or I/O prompting.
Okay.
You ask a question, the model answers. That's the raw System 1. You give it the input, solve this math problem, and it tries to spit out the answer in one continuous breath.
The Hail Mary pass. You throw the ball and hope the model catches it in the end zone.
Right. And for anything complex, the ball usually lands in the parking lot.
So then what? What was the first fix?
Then we had the first major evolution, chain of thought or copy. This was the big breakthrough where we realized if you tell the model think step by step, performance improves massively.
Right. Instead of just asking for the answer, you ask it to show its work. First I do this, then I do that, therefore the answer is X.
Correct. By forcing the model to generate those intermediate steps, you are effectively giving it more compute time to process the logic. You are spreading the reasoning out over more tokens.
Okay, that makes sense.
And this is the big, but chain of thought is still linear. It is still a straight line from A to B.
It's a longer line, a more detailed line, but it's still a single path.
Exactly. If one link in that chain snaps, if the model makes one calculation error in step 2 of 5, the whole solution collapses.
Yeah.
The model, being autoregressive, will just look at that error in step 2 and treat it as a fact for step 3. It creates a domino effect of failure. There is no recovery mechanism.
And then there's self-consistency, right? That was the next attempt to fix this brittleness.
Yes, cut self-consistency, or cut TSC. That's basically taking the chain of thought approach, running it, say, 100 times in parallel.
And taking the majority vote. So throw enough spaghetti at the wall and see what sticks. If 70 out of 100 times it says the answer is 42, it's probably 42.
Essentially, it adds diversity and it helps drown out the random noise and the hallucinations, but it lacks local exploration.
What do you mean by local exploration?
It's just running the same linear process multiple times. It doesn't allow the model to plan within the chain. It can't say, this first step feels shaky, let me consider 3 other first steps. It's just hoping one of the full chains gets lucky.
It's brute force.
It's brute force, not intelligence.
Okay, so enter the tree of thoughts. How does this change the game? How do we move from throwing spaghetti to actually, cooking a meal?
The shift is geometric. We are moving from a line, a chain, to a tree.
Okay.
Imagine a decision tree. You have a root node, which is your problem. From that root, you don't just generate the next sentence. You generate multiple possible next steps.
Okay, so instead of just writing the next sentence, I brainstorm 5 different ways I could write the next sentence.
Exactly. Those are the branches. The nodes in this tree represent partial solution states of the problem. The branches are the operators or actions that modify those states. It turns the problem-solving process into a map.
A map, I like that.
You are at point A. You could go north, south, east, or west. Standard chain of thought just picks north and starts walking. Tree of thoughts looks at all 4 directions, takes a few steps down each, checks the terrain, and then decides.
And the paper defines something called the thought unit. What counts as a thought here? Because thought is a pretty abstract concept.
That is one of the key design decisions, and it depends on the problem.
So it's not a fixed thing.
No, it's flexible. If you are doing a crossword puzzle, a thought might be filling in a single word. If you are solving a math problem, a thought might be one intermediate equation.
And for something like writing.
If you are doing creative writing, a thought might be a 1-sentence plan for the next paragraph. It's a coherent chunk of language that serves as an intermediate step.
So it's the atomic unit of reasoning for that specific task.
Right. And the Tree of Thoughts framework, or 2T, breaks this down into 4 specific modules. If you want to build this agent, you need 4 things. It's like a recipe for a system 2 brain.
Okay, let's walk through them. What is the first ingredient?
First is thought decomposition. You have to teach the agent how to break the problem into these steps.
Right, the model doesn't just know.
Exactly. You can't just say solve it. An LLM doesn't inherently know that a math problem needs to be broken down into lines of algebra. You have to structure the prompt to explicitly ask for these intermediate steps.
So you're teaching it the rules of the game. Don't try to eat the whole steak in one bite. Cut it up.
Exactly. Once you have the problem decomposed, you need the second module, the thought generator. This is how the agent creates potential next steps. The paper suggests 2 strategies here. Strategy A is sample independent thoughts.
Okay.
This is great for rich, creative spaces. You just ask the model to generate 5 different versions of the next paragraph, for example.
It's brainstorming. Give me 5 ideas. No judgment yet.
Right. And strategy B is propose thoughts sequentially. This is better for constrained problems like math or crosswords, where the space of possible answers is tighter.
Why is that better?
Because you can ask the model, given the current state, propose possible next words that fit. It avoids duplication and keeps things tight and focused.
Okay, so we have broken the problem down and we have generated a bunch of options for the next step. Now comes the magic part, right?
I would say so.
Because if we just keep generating 5 options for every step and 5 options for the step after that, the tree explodes. It gets way too big. We can't keep everything.
Precisely. We need a filter. And this is the third module, the state evaluator.
The judge.
The judge. This is the deliberate heuristic. This is the system 2 kicking in. We need the model to look at these 5 options it just generated and judge them.
And ideally, in a perfect world, we'd use a calculator or a code compiler to judge them.
Right.
Something grounded in truth.
In a perfect world, yes. And for some tasks, you absolutely can use external tools. But the big innovation here is using the LLM as the evaluator.
Okay, hold on.
The paper argues that LLMs are capable of self-correction if you frame it correctly.
So you're telling me the thing that just generated the options is now going to critique them?
Yes. They propose 2 ways to do this. Method A is valuation. You ask the model to assign a scalar score, like 1 to 10, or a classification, sure, likely or impossible, to each state.
So the model looks at its own work and says, this path looks like a dead end, I give it a 2. This path looks promising, I give it a 9.
Exactly. And method B is voting. You present the different states to the model and say, compare these options and vote for the best one.
This seems wild to me. We are trusting the model, which we know hallucinates, to catch its own hallucinations. It feels like asking a liar to fact-check themselves.
It does feel counterintuitive, but it turns out LLMs are often better critics than they are creators.
Really? Why would that be?
Think about it from a human perspective. It is much easier to read a paragraph and say, that doesn't make sense, than it is to write a perfect paragraph from scratch. It is easier to verify a solution than to find it.
That's a great point. I can spot a typo way easier than I can write flawless prose.
By separating the generation step from the evaluation step, you allow the model to switch modes.
That's fascinating. So it generates in system 1, mode fast, loose, creative, then evaluates in system 2, mode critical, analytical, judgmental.
Correct. You are bifurcating the personality of the model. And then we have the 4th and final module, the search algorithm.
The driver.
This is the engine that drives the car. How do you navigate this tree you are building?
And they use the classics here, right? This is straight out of a computer science 101 textbook.
Breadth first search, BFS, and depth first search, DFS. These are the standard ways to traverse a graph or a tree.
Let's explain those for the listeners who might have skipped that particular class.
Sure. Breadth first search, or BFS, explores layer by layer.
Like a wave.
Like a wave spreading out. You generate all options for step 1, you evaluate them all, you pick the best few, say the top 5, then you generate all options for step 2 based on those top 5. You move forward on a broad front.
And that's good for what kind of problem?
It's good when the solution isn't too deep or when you want to keep your options open, like in creative writing.
Okay, and DFS, depth first search.
Depth first search is for the hard stuff.
Yeah.
The complex logical puzzles. You pick the most promising path and you dive deep.
All in on one bet.
For a moment, yes. You go to step 1, step 2, step 3, all the way down. But, and this is absolutely crucial, if you hit a dead end, if the evaluator says, impossible, you stop.
Yeah,
you backtrack. You go up the tree to the last decision point and you try a different branch.
That word backtrack. That is the holy grail. That feels like everything.
It is. It's the whole game.
That ability to say, oops, wrong turn, and go back.
Yeah.
That feels like the definition of intelligence to me. Standard LLMs just plow straight into the wall. This architecture allows them to reverse.
It is the definition of planning. You cannot plan if you cannot correct your course.
All right.
If you are driving and you miss your exit, you don't just keep driving into the ocean. You turn around. Standard chain of thought is the car that drives into the ocean because it refuses to turn the wheel.
Okay, so that's the theory. And it sounds incredible on paper. But does it actually work? Because we've seen a lot of these reasoning papers that turn out to be hype.
The proof is in the pudding.
And this paper throws 3 specific, very different challenges at this architecture. Let's dive into the experiments. The first one is the game of 24.
Yes, the game of 24. It's a classic arithmetic game often used to teach kids math fluency.
Okay, how does it work?
You get 4 numbers, say 4, 9, 10, and 13. You have to use basic arithmetic, add, subtract, multiply, divide to make them equal exactly 24.
And you have to use each number exactly once.
Exactly once. It sounds simple, it's just elementary math, but it's actually really tricky because of the combinations.
It requires look ahead.
Absolutely. You can't just greedily pick the biggest numbers. For example, with 4, 9, 10, 13. If you just say 10 plus 13 is 23, you are very close to 24.
Which feels like a good move.
It feels like a great move, but you have a 4 and a 9 left. There is no way to turn a 4 and a 9 into a 1 to finish the problem. You've painted yourself into a corner.
You optimized for the short term and failed the long term. A classic blunder.
Precisely. So how did standard GPT-4 do with just chain of thought prompting? They gave it the numbers and said, think step by step and solve.
I'm guessing not great, given the buildup.
Terribly. The success rate was roughly 4%.
4%. That is basically random guessing. That is abysmal.
It's awful. Essentially, the problem is that standard COTI often fails early. It will say 4 + 9 = 13, and then get completely stuck because it can't make 24 with the remaining numbers.
And it can't go back.
It can't go back and undo that first addition, so it just hallucinates a wrong answer at the end to try and make it fit. It will say 13 + 10 + 1 = 24, even if there was no 1 in the original set.
So it doubles down on the mistake. It gaslights you. I made 13, so over there, 24.
Exactly. Now compare that to the tree of thoughts implementation. They used a breadth-first search, keeping the best 5 candidates at each step. So at step 1, it considers adding 4 + 9, 4 + 10, 4 + 13, 9 + 10, and so on. It evaluates all of them.
And the result?
The success rate jumped to 74%.
Hold on. From 4% to 74%.
From 4% to 74%.
That is not an incremental improvement. That is an exponential leap. That is the difference between a toddler and a math student.
It is huge. And the error analysis tells exactly why. In COTI, most errors happen at the very first step. The model picks a bad starting move.
Right.
In TOTI, the model can look at that first step, evaluate it, and realize, wait, if I do 4 + 9, I'm left with 13, 10, and 13. I can't get to 24 from there. And it prunes that branch immediately.
It stops the mistake before it cascades, before it becomes a problem.
Precisely. It wastes no compute on a dead end.
Yeah.
It focuses its energy only on the paths that the evaluator deems likely or possible.
Okay, so that's math. Math is rigid. It has a single right answer. But what about something more subjective? The second experiment was creative writing.
This one was really interesting because it tested constraint satisfaction in a creative domain. The task was to write a coherent passage, but it had to end with 4 specific predetermined input sentences.
So it's like a puzzle. Here are 4 random sentences. Write a story where paragraph 1 ends with sentence A, paragraph 2 ends with sentence B, and so on.
Right. And these sentences were random, so you might have to connect the sun set beautifully over the ocean with the stock market crashed violently in a way that makes narrative sense.
That requires high-level planning.
Immense planning. You have to think backwards from the end of the paragraph to the beginning. You can't just write.
And how did 2T handle this? What was the setup?
They used a decomposition strategy. First, the agent generates a plan. Not the text, just the plan. Something like, paragraph 1 will be about the character leaving work feeling optimistic. Paragraph 2 will be about him checking his phone and seeing the bad news.
Smart. Separate the plotting from the writing. That's what human authors do.
Yes. Then it generates 5 different plans. It votes for the best plan. Then, based on that one winning plan, it generates 5 different passages and votes again for the best passage.
So it's a tournament bracket for thoughts. Only the strongest ideas survive to the next round.
That's a great way to put it. It's iterative refinement.
And the results. How did it do?
The results showed that humans preferred the TOTI outputs over the standard COTI outputs in 41 out of 100 pairs.
That sounds, okay, 41 out of 100. That implies that in 59 cases it was either tied or COTI was better.
Well, you have to remember that in many cases, especially with easy sentences, both methods produced perfectly acceptable results. So there were a lot of ties.
Oh, okay.
But the key metric was coherence. When the sentences were really disjointed, standard COTI would often just write nonsense to bridge the gap. It would veer off topic. TOTI was significantly more coherent. It didn't drift. It stayed on the rails because it had a plan.
So it provides a floor for quality. It prevents the model from wandering off into the weeds when the problem gets hard.
Exactly. It's more reliable. Okay, now let's talk about the final boss, the mini crosswords.
Right. This is the one.
This, to me, is the most impressive part of the paper. They took a 5x5 crossword puzzle. Now, crosswords are incredibly hard for AI.
Why is that? It seems like it's just knowledge retrieval. Capital of France, Paris, easy enough.
It's not just retrieval, it's topology. The constraints interact horizontally and vertically.
Oh, of course.
If you put a word in one across, it changes the possibilities for 1 down, 2 down, 3 down. If you pick the wrong word for 1 across, even if it perfectly matches the clue, you might make 3 down completely impossible to solve.
It's a dependency nightmare. Everything is connected to everything else. You change one thing and it ripples across the whole grid.
Exactly. And standard GPT-4 with chain of thought, well, It was not good. It achieved a word-level success rate of about 16%.
16%. Ouch.
It would fill in words that fit the clue, but completely broke the crossing words. It just couldn't see the grid as a whole. It was solving each clue in isolation.
It was playing Scrabble by itself, ignoring the board. I have a great word here. Yeah, but you can't put it there. There's a Q and you need a vowel.
Perfect analogy. So for 2A, they use depth-first search, and this is where the pruning mechanism really, really shines. This is the killer feature.
Pruning. That's the gardening term. Cutting off the dead branches.
Yes. In the algorithm, before the model fills in a word, it looks at the remaining grid. It asks itself a critical question. If I put the word apple-e here for one across, does that make any of the remaining clues impossible to solve?
Oh, that is clever. So it checks if apple-e creates a situation where 3 down needs to start with QP or something impossible in the English language.
Exactly. It uses the LLM to scan the future state of the board. If the model sees that a choice makes any future step impossible, it prunes the branch immediately. It doesn't even try to fill the rest of the grid with that word. It backtracks and tries a different word, maybe ALCHA.
And the results?
The word level success rate jumped to 60%.
16% to 60%. Yeah. Again, that is a massive, massive jump.
It's night and day. And the key takeaway here is the significance of saying no. The ability to look at a path and say, this leads nowhere, and then stop. That is the defining feature of agentic intelligence versus generative babble.
Generative models always want to say yes.
They always want to say yes, and agents need to know how to say no.
It feels like we are seeing the birth of self-correction. We are seeing the model acting as a logical entity, not just a linguistic one.
We are, but we have to talk about the cost. We can't gloss over that.
Yeah, I was going to ask. Generating 5 options for every single step, voting on them, backtracking, checking the board state. That's a lot of tokens. That's a lot of GPU burn.
It is. The paper is very upfront about this. It notes that 2T requires significantly more computation than standard prompting. For the game of 24, it was something like 100 times the cost in terms of tokens generated.
100 times. Ouch. Yeah. So you're not going to use this to write your grocery list?
Yeah. No, you absolutely should not use free of thoughts to ask, what is the capital of France?
Oh.
That is a System 1 task. You waste an enormous amount of energy engaging System 2 for that.
This brings up the efficiency versus intelligence trade-off.
Exactly. For simple, everyday tasks, System 1 just asking the model is fine. It's cheap and fast. But for complex tasks where accuracy is non-negotiable...
Like what?
Like medical diagnosis, legal reasoning, or coding critical infrastructure,
yeah.
The cost of System 2 is not just worth it, it's necessary.
It's the difference between asking a friend for a movie recommendation and hiring a consultant to restructure your business.
Yeah.
You pay for the deliberation, you pay for the hours they spent thinking about the problem.
Exactly. And the beauty of this framework is its modularity. You can plug and play.
What do you mean by that?
You can use different search algorithms. You could swap in a search or Monte Carlo tree search. You can swap out the evaluator for a different model or a tool. You don't need to retrain the underlying LLM.
That's a huge point. This isn't a new model architecture. It's a new inference architecture. It's a way of using the tools we already have much more effectively.
Yes. You don't need access to the model weights. You just need API access to something like GPT-4 or Claude.
It democratizes this kind of agentic research.
It does. And it connects back to the history of AI. We are seeing a merger of the symbolic AI of the past. Things like search, planning, logic trees.
The stuff that beat Kasparov in chess.
Right, with the connectionist AI of the present neural networks and LLMs. 2T is the bridge between them.
It's using the neural net as the intuitive engine for the symbolic search. It's the best of both worlds.
Perfectly put. For a decade, symbolic AI was considered, dead. Neural nets ate the world. But now we are realizing that neural nets are intuitive but messy. By reintroducing these symbolic structures, trees, search algorithms, we are giving the neural net the structure it needs to be reliable.
So we have established that tree of thoughts is a massive leap forward for reasoning. It turns a text generator into a planner. It allows for backtracking, it allows for self-correction. But where does this go next?
Ah, the fun part.
I think it's time for our favorite segment. We've looked at the paper, now let's look at the horizon.
Let's do it.
Novel notions.
Disclaimer. The following ideas are for entertainment purposes only and represent speculative scenarios based on the paper's architecture. These do not exist yet, but they probably should.
Okay, I have an idea. I'm really excited about this one. I call it the counterfactual coder.
I like the sound of that already. Break down the mechanism.
Okay, so we saw in the crossword puzzle that the agent prunes branches that lead to impossible board states. It sees that a word choice now will break the puzzle 3 steps later.
Right, the look ahead.
What if we apply that exact logic to software engineering?
Go on.
Right now, coding agents just write code. They are fancy, autocomplete. Sometimes it compiles, sometimes it doesn't. Often they introduce technical subtle bugs that won't bite you until 3 files later.
The worst kind of bugs.
But imagine a TOTI agent using depth-first search. It's tasked with writing a complex new feature. Before it writes a single line of actual code, it generates a thought tree of architectural decisions.
Okay, so it's planning the architecture first, not just the code.
Exactly. Big picture stuff.
Ugh.
Should I use a SQL database or no SQL for this feature? Should I use this third-party library or that one? For every decision point, it runs a state evaluator. But here's the twist. The evaluator isn't just checking for syntax. It's running a mental compiler or security critic prompt.
Ah, I see where you're going with this. It simulates the future state of the entire repository?
Yes. The agent simulates the implementation path. It asks itself, if I choose to use SQL here, will I run into a scaling bottleneck in step 5 based on the user requirements? If the evaluator prompt comes back with likely, it prunes the branch. It effectively debugs the code before it's even written. It's pruning future bugs.
That is compelling. It is applying the crossword impossibility check to architectural decisions. It's preventing you from painting yourself into a coding corner, which is like 90% of software development.
Exactly. It's saying, no, don't use that library. It's going to conflict with the dependency you absolutely need in step 10. A standard chain of thought agent would just write the code, get to step 10, and crash. The counterfactual coder avoids the crash by seeing it coming.
That is a very, very strong application of the pruning concept. It moves the IDE from being a text editor to being an active reasoning environment.
It becomes a collaborator.
A true collaborator. Okay, I have one that takes the creative writing voting mechanism and applies it to game theory.
Ooh, let's hear it.
I call it the diplomatic simulation engine.
Sounds intense. Is this for world peace or hostile corporate takeovers?
Both. Why not? Imagine a multi-entity negotiation bot using 2T with breadth-first search. Let's say you were negotiating a complex contract or even a peace treaty. The stakes are very high.
Okay, with you.
At each turn, the agent generates, say, 5 potential offers or moves. That's the thought generator. But then, for the evaluation phase, it doesn't just vote on which offer sounds nicest.
It does what?
It simulates the opponent's reaction to each of the 5 offers.
Look ahead. It's modeling the other mind.
Yes. It creates a temporary opponent agent, a persona modeled after the person you are negotiating with, based on their past actions, writings, personality profiles. It plays out the timeline for each offer 3 steps into the future.
Wow.
So it thinks, if I offer X, they will likely counter with Y, and we end up at state Z. But if I offer A, they will get offended and likely leave the table.
It creates a multiverse of negotiations, a decision tree of possible futures.
Exactly. It creates parallel timelines. It then votes on which timeline leads to the best long-term outcome for you, executes that move in reality, and then repeats the process for the next turn.
That is basically Doctor Strange in Infinity War, checking 14 million outcomes to find the one where we win.
Ideally with fewer Thanos snaps. But yes, that's the concept. It moves the voting from being about static quality, is this paragraph good, to being about dynamic utility, does this move win the game?
That feels incredibly powerful and also slightly terrifying, if I'm being honest. It weaponizes empathy and simulation.
As all good AI concepts are. But it shows the power of the architecture. Tree of Thoughts isn't just about solving puzzles on a piece of paper. It's about simulating the future to make better decisions in the present.
So to wrap this all up, Tree of Thoughts, it is not just about getting better scores on math problems. It is about a fundamental architectural change.
It is. It is about acknowledging that thinking, real thinking, is not a straight line. It is a branching path.
Full of wrong turn.
It involves dead ends, backtracking, and deliberation. If we want agents that can truly operate in the real world, they can't just be autoregressive babblers. They have to be planners.
They need a system too.
They need a system too.
And Tree of Thoughts gives them exactly that. It transforms the AI from a yes man into a thinker. Thank you for listening to Talk Tensors. This has been a deep dive into the architecture of reasoning.
Keep thinking.
And we will see you on the next branch.